Hey science students, it's Leslie from Tesla Tuition Videos, and today we are doing the physics topic of forces in equilibrium. Okay, let's get started. So the first thing I'll say about equilibrium is that this actually is part of Newton's first law of motion. The concepts of today's lesson will also be what we use to do Newton's first law calculations. Now, a good place to start with this would be to ask ourselves, what is equilibrium anyway? Now, the word equilibrium, it kind of has the word equal in it, and it reminds me of balance, things being balanced or in equilibrium. And that kind of explains what it is as well. Equilibrium describes a state of an object where all the forces acting on that object are balanced, so that the net or resultant force acting on the object will be equal to 0 newtons. Now you'll see I've written a very similar definition for equilibrium here on the board. All forces acting on an object are balanced so that the net or resultant force acting on the object is equal to 0. Now, objects that are in equilibrium have one of two types of motion. Either they are at rest or stationary or not moving, in other words, or they are moving at a constant speed or velocity. Now, in both of these cases, you are not having any acceleration, which is also the theme of Newton's first law of motion. In order to have acceleration, velocity needs to change over time. So if it doesn't change, if it stays constant, or if an object is just remaining stationary, it means there is no acceleration. And if there is no acceleration, it means the net or resultant force acting on an object is equal to 0, which is the whole idea behind equilibrium. Okay, let's carry on. So what does it even mean for forces acting on an object to be balanced? Well, it simply means that all the forces going in one direction, if you added them up, are going to be equal in magnitude or amount to all forces going in the opposite direction. And this is going to be true in both the x direction, which is usually parallel to the surface, that is also known as the horizontal, and it will also be true vertically in the y direction, which is usually perpendicular to a surface. So, for example, if all forces up equal all forces going down, and all forces left equal all forces going right, then the forces all cancel to give a resultant or net force of 0 newtons. And that is what is happening in equilibrium. Now, the fact that forces in opposite directions are equal in magnitude or amount is what we will actually use to solve for certain unknowns with questions related to equilibrium. So with a story in equilibrium, you literally add up all the forces going in a certain direction, and that can include x and y components of angled forces. Now, you will know a system is in equilibrium because the story will tell you that the system is in equilibrium usually, or they will tell you that the object is remaining at rest or stationary or moving at a constant velocity. Let's look at an example now. Right, so I've given an example of a question on the board here, but we're not going to actually work through this calculation. I haven't given any values for the forces. We're just using the scenario to help us better understand what an equilibrium question kind of looks like and what does it kind of mean. So the question reads, or example, an object of mass m hangs from the ceiling by 2 ropes at an angle. The tension in the first rope is T1 and the tension in the second rope is T2. The system is in equilibrium. Now, before we move on and look at the diagrams, I should tell you that the majority of equilibrium questions in grade 11 and grade 12 deal with objects that are usually stationary with three main balanced forces acting on them. Now, this example here says the system is in equilibrium, but sometimes they don't tell you that, and you have to kind of know that it's equilibrium from the story. This is a system that's hanging at rest or stationary, where the ropes form very specific angles, which can only be if the object is stationary. And that tells me, okay, this is an equilibrium situation. Now, they almost always give diagrams for questions in equilibrium, and here's the diagram here. So at the top here is the ceiling or the roof, and in this particular case, I've decided to include two angled forces, tension 1 or T1 and tension 2 or T2. But sometimes there is only one angled force in an equilibrium story. Here we have two, but please be careful because the diagram does not show all the forces acting on the object. Now, friendly reminder, tension is a type of force that you can find in a string or cable or rope. And tension in a rope or cable or string is always pulling away from the object. Now, in this case, I've given you two little angles just to remind us that T1 and T2 are at an angle. And here is a block of unknown mass M. Now, we can do a free body diagram of the forces acting on the object, but we will have to know that the missing force from the diagram is going to be force of gravity, also known as weight. So if we come over to this side now, my first option of a free body diagram shows three forces. We've got here tension 1 pulling away from block M in this direction, and we've got tension 2 pulling in that direction, and force of gravity, also known as weight, is going straight down. Now, there is actually another correct option of a free body diagram that we can draw for this situation, which is actually going to be essential for us to understand which forces are equal to which other forces. Now, that is because most equilibrium questions involve at least one force at an angle, and you need to always remember to break down your angled forces into X and Y components that you can also show on another option of free body diagram that we are going to look at now. Okay, so what I've done is copied the free body diagram from the previous board, and now we're going to see the other correct option of free body diagram for this example. Now, this diagram here is perfect for full marks, but if you give this diagram, then please do a version of the free body diagram for yourself, even if it's on a scrap piece of paper that shows the components. I can tell you that free body diagrams showing components are way more useful for calculations than the free body diagrams that don't show them. So many of my students will give, for example, this version for full marks in a tester exam, but then they will sketch the version of the free body diagram that has the X and Y components for themselves on a piece of paper, and they'll work off that one to do the calculations. So if my force T1 goes there to the left and a little bit up, then its X component T1X will be going to the left, and its Y component T1Y will be going up. I've shown them in pink on this diagram. Now, T2, on the other hand, is going in this direction, diagonally up and to the right, and that gives us the direction of its components. So the X components of T2, called T2X, that goes to the left, and its Y component T2Y goes up. Right, I've drawn those in green. FG, or weight going straight down, has not changed. So now let's think about which forces are equal to which other forces for the objects in equilibrium. We can only use this version of the free body diagram with the components to see which forces are equal to which other forces. Now, when I make forces in opposite directions equal, I first start by mentioning that F net is equal to 0 newtons. It's kind of like my reason for then making forces equal to each other. Now, F net's equal to 0 for this object in equilibrium. So forces going to the left must be equal to forces going to the right. That means, therefore, that T1x going to the left has to be equal in magnitude to T2x going to the right. Now, you can even expand the formula by using the formulae for T1x and T2x respectively. Remember that T1x as a formula would be equal to T1 cos theta. Now, in my lesson on components of angled forces, we discussed the formulae for x and y components. So check that out if you haven't already done so. Now, T2x can be expanded as T2 times cos theta. Now, these thetas are not necessarily the same angle. It will be the horizontal angle that each rope makes with the x-axis or horizontal. Okay, so now what about the y direction? Well, in the y direction, it is not true or not correct to assume that T1y and T2y are equal. They might be, but they don't have to be. But what is true for equilibrium is that all forces going up are equal in magnitude to forces going down. So what would be true to say, and I'll write it on this side, is that the sum of the forces going up, so T1y plus T2y, both going up, that would be equal to our force going down, which is Fg, or if you prefer, W for weight. Okay, so T1y plus T2y, both going up, would be equal to force of gravity going down. And once again, as a starting statement, you really should say F net equals 0 newtons. Never too late to fill it in. Right, so now I can expand this formula as well by using the component formulae for T1y and T2y, but I can also expand Fg as m times g as well. So expanded now, T1 sine theta is the expanded version of T1y, and T2 sine theta is the expanded version of T2y. And that's going to be equal to m times g, which is Fg expanded. Next, let's move on to another type of force diagram that can be drawn for 3 forces in equilibrium. This diagram is typically called the closed triangle of forces. Let's see what that would look like for this example. Now, sometimes in an equilibrium question, they will ask you to draw what they call a closed triangle of forces. Now, just to help us, we have included one of our previous free body diagrams. Now, to help with your closed triangle of forces, you want the free body diagram that doesn't show components, but rather the 3 main balanced forces on an object. Now, the closed triangle of forces will have each force represented as an arrow, and they're all going to be drawn head to tail. So what I usually like to start with is Fg going straight down. Okay, so for my first possible closed triangle of forces, I'm going to draw my force of gravity going straight down like so. Now, I need to draw the next force starting with its tail at the head of Fg. Now, I can pick T1 or T2, but for my first version, I'm going to do T2 going in this direction here. So I start there, and now this is going to be T2. Finally, I'm going to fill in my T1, and T1 is going to close the triangle, ending with its arrowhead at the tail of Fg. So here we go. There it is. T1. Right, now another version of this closed triangle of forces could be a bit of a mirror image of this where it's not exactly the same as this one. So for this one, I'm going to start with FG again, going straight down. But for this one, I'm going to draw T1 going in that direction where it's going like so. And then finally, T2 will close the triangle. And there you have it, your other possible version of the closed triangle of forces. Sometimes they want you to also include angles in your closed triangle of forces. And not always, but sometimes your closed triangle of forces will even be a right angle triangle with a 90-degree angle at one of the corners. But please do not just assume that your triangle will be a right angle triangle. It does not have to be. Okay, that brings us to the end of today's lesson on forces and equilibrium. Head over to our website for our full-length science videos.